Hello everyone, I am Erkal Hemteja, a master student in computer science. I created an interactive application using C++, OpenGL, and ASIMP. This application can simulate a virtual environment, rendering realistic graphics, and allows users to manipulate 3D objects. I faced challenges in software design and algorithm optimization, but was able to complete it successfully. And outline. My project was developed using C++ and OpenGL and ASIMP, and it features texture mapping, transformations, camera movements, lightning, light casters, a space background, and astronomical events. I included a demonstration of the application capabilities. Or C++ and OpenGL. C++ is a versatile programming language that can be used for developing a wide variety of applications. One popular use case is for creating computer graphics, which is more, which, which is where OpenGL comes in. OpenGL is a graphics API, our application programming interface that is used in conjunction with C++ to render 2D and 3D graphics in applications. Together, C++ and OpenGL provide developers with a powerful toolset for creating visual, stunning, and interactive software. ASIMP. ASIMP or Open Asset Import Library is a powerful cross-platform library that allows for the loading of 3D models in various formats into C++ applications. With support for a wide range of file formats including OBJ, FBX, and Collada, ASIMP provides developers with a versatile toolset for incorporating 3D models into their applications. By leveraging ASIMP, developers can more efficiently, easily, and effectively create visual, stunning, and immersive software experiences. And next we discuss about texture mapping. And texture mapping is a popular technique used in computer graphics to apply texture to a 3D object. By mapping an image onto the surface of an object, it can be made to appear more realistic and detailed. In our solar system project, we utilize texture mapping to apply high quality images of planets and other celestial bodies to their corresponding 3D models. This allowed for a more impressive and visually engaging experience for the users and helped to make our project feel more like to true representation of a solar system. And next we're going to discuss about transformations. Transformations are a fundamental concept in computer graphics used to manipulate the position, orientation, and scale of a 3D object. In our solar system project, we utilized a variety of transformations, including translations, rotations, and scaling to position and orient planets and other celestial bodies in space. By using these transformations, we were able to accurately represent the size, distance, and relative position of each object in the solar system. Transformations are a critical tool for creating realistic and immersive 3D environments, and their use was integral to the success of the project. Next, we are going to discuss about camera. So, the camera is an essential tool in computer graphics used to navigate and view 3D scenes. In our solar system project, we utilized a camera to view the planet and other celestial bodies from different angles and distances. By manipulating the camera position and orientation, users were able to explore the solar system and use it for the various perspectives. The camera provided a critical element of interactivity and immersion in our project, allows users to feel like they were truly exploring space. The use of a camera is a key concept in 3D graphics and is an important tool for creating dynamic and engaging visual effects. Lightning. Lightning is a crucial element in computer graphics used to illuminate 3D scenes and make them appear more realistic. In our solar system project, we utilized various lightning techniques to stimulate the behavior of light in space. Especially, we used the Phong optical model to calculate the deflection and scattering of light on the surfaces of planet and other celestial bodies. By accurately simulating the behavior of light, we were able to create a more realistic and immersive experience for users. Lightning is a fundamental concept in 3D graphics and is a critical tool for creating visually engaging and interactive software. Next, we're going to discuss about light casters. Light casters are a critical tool in computer graphics used to create various lighting effects in 3D scenes. In our solar system project, we utilize different types of light casters, including directional lights, point lights, and spotlights with soft edges to create realistic lighting for the planets and other celestial bodies. By using different types of light casters, we were able to accurately stimulate the behavior of light in space and create a visually engaging and immersive experience for users. The use of light casters is a key concept in 3D graphics and is an important tool for creating realistic and dynamic lighting effects. Space background. The space background is a critical component of a 3D scene used to create a realistic environment. In a solar system project, we utilize a space background consisting of images of stars and galaxies to create a more immersive and engaging experience for users. By accurately representing the vastness of space, we were able to create a more realistic environment for our celestial bodies to exist in. The space background is an essential element in any space-related 3D graphics project and can significantly impact the overall user experience. Astronomical events. The solar system is home to a wide range of fascinating astronomical events, including eclipses, conjunctions, and transits. In our solar system project, we included the option to stimulate these events using C++, OpenGL, and ASIMP. Especially users could simulate solar eclipse and other astronomical events, providing a more engaging and interactive experiences. By incorporating these events into our project, we aim to create a more educational and immersive experience for users, allowing them to learn about the wonders of our solar system in a fun and interactive way. The ability to stimulate uh, the the ability to stimulate astronomical events is an essential feature for any space-related 3D projects and can significantly enhance the overall user experience. And implementation, if you go to the implementation details, in our solar system project, most objects include the background and are rendered as sphere models using the sphere.obj file. Additionally, we implemented the Phong optical model for lighting calculations, including the ambient and diffuse parts in the fragment shader named lighting.frag. We use a single point light source, which is the sun, to achieve a realistic lighting effect. For rendering moons, we use the model matrix of the parent body to ensure correct positioning. We also implemented the rendering of Saturn's rings as a disk model using the ring.object file and enabled a suitable blending mode for transparency. To achieve the bright glow effect around the sun, we used a semi-transmit enlarged sphere and implemented it in the sunglow.fragment shader. The transparency of the glow is determined by the viewing distance of the sun. We also enabled a suitable blending mode and curl front faces for correct rendering. The solar eclipse effect was achieved by setting the camera position where the sun and the moon have the same angular size for animation. We slightly rotated the camera around the sun during the eclipse. This implementation details helped us to create a realistic and engaging solar system. Research. In our solar system project, we conducted research to ensure the accuracy and realism of the astronomical objects. We used the planetary fact sheet ratio to Earth values from the National Space Science Data Center website to gather data on the planets and their characteristics. We also obtained high-resolution textures for all astronomical objects for the website Solar System Scope. In addition, we used tilt angles of rotation axis for planets and major moons with arbitrary parameters to simulate realistic movements. The research was crucial in ensuring the accuracy and authenticity of the project. In conclusion, our solar system project demonstrates the use of various 3D graphics techniques and tools, including texture mapping, transformations, lighting, and space simulations. The 3D solar system project is a great example of how C++, OpenGL, and ASIMP can be used to create realistic 3D graphics and animations. It demonstrates the power of these technologies and the potential they hold for creating stunning visual experiences. We hope you enjoyed our presentation and thank you for your attention. Now, let's go to the demo of this project. So, this is the let me reset the camera. So, this is the initial view of our project. So, we are in the solar system and here we pointed to the center of the sun. So once we start rotating once we start pressing the key R, the planets start rotating around the sun and we can reset this by clicking the reset button. Just a moment. Let me run this again. So this is the initial view, and when we click the button R, we start rotating around the sun, and on clicking button P, we pause the rotation of the uh, planets around the sun. So on clicking R, it rotates, and on P, it pauses. And we have a feature of zoom in and zoom out for the space for the camera view. So on pressing the button S, we zoom out the view, and on pressing button W, we zoom in. So thus we can view the closer picture of the planets. And on pressing the buttons A and D, we direct the camera to move to the left or right. A represents the left and D represents the right. And using the mouse button, we can change the angle of the camera to view the objects in the specific region. So we can move up and down, left and right. We have 360-degree axis to the mouse event. So I'm zooming to the Jupiter. No, it's a Saturn, sorry. So here you can see this has moons aligned around the planet in a specific distance, and on pressing R, these start rotate around the planet, and the planet is also revolving around the sun. And we have implemented the solar eclipse, where we can see that moon is covering the sun here, and this is a continuation video where this goes on to show how the solar eclipse happens. And we can pause this event to see how this is happening, and we can see that moon is covering the sun. On clicking reset, the process again starts from the beginning. On clicking the reset camera button, we can reset the position of the camera again. So once we zoom out or zoom in somewhere in the space, we can click the reset button to set the camera to the same original position. Thank you.